everyone. I'm Geordie Williamson. I'm the director of the Sydney Mathematical Research Institute that's hosting this event. So before we begin, I would like to acknowledge the Gadigal people of the Eora Nation. Part of the public lecture is about teaching and learning, and teaching and learning has been happening here where we're standing for thousands and thousands of years. So we're really delighted to be hosting Frank Calegari. This is the first lecture of the Mahler Lecture series. So Kurt Mahler, the famous number theorist in the 20th century, and he spent part of his career in Australia. And when he died, he left some money for a lecture series, which has been running, I believe, since 1991. The Mahler Lecture series attempts to attract the best mathematicians in the world who are working in areas not too far away from the areas where Mahler was a specialist, mainly around number theory and related fields. So we've had Australian fields medalists Terry Powell and Akshay Venkatesh, Peter Sarnak, Holly Krieger, former Mahler lecturer. So Frank Calegari is, I think, one of the best Australian mathematicians that's currently alive. He's a professor at the University of Chicago. So someone said, "Who is Frank?" a couple of weeks ago. They said, "Who's this guy, Frank Calegari, who's giving this Mahler lecture?" And three things came to mind: mathematics, coffee, and classical music. I think he's a specialist in all three. You know, certainly knows a lot more about coffee than I do. Frank has many distinctions. So he was an American Institute of Mathematics fellow. He's a postdoc awarded to exceptional young researchers. I believe it's 5 years. 5 years of yes. He's a fellow of the American Mathematical Society. And this year we had the International Congress of Mathematics, where Frank was accorded the honor of being a plenary speaker. And because of the geopolitical situation, the ICM happened largely online. And so Frank has produced an exceptional video on the modularity, so Fermat's last theorem and related developments. So if you enjoy the lecture tonight, I'd really recommend watching Frank's wonderful lecture. So yeah, thank you all for coming. Thank you very much and welcome, Frank.
So thank you, Geordie, for the introduction. It's a great honor to be giving these Mahler lectures. Mahler certainly proved some very interesting results about pi, although I won't touch on them today, but actually have a more personal connection to the Mahler Lecture Tour. In 1993, this is going to age me, I played truant from high school and attended the Mahler lecture of Don Zagier at Melbourne University. And it had a big effect on me. And 25 years later, I then wrote a paper with Don Zagier. So if there are any high school students in the audience today, I hope that we'll be writing papers together in 25 years' time. So my talk is on the secrets of pi, but there's a secret subtitle to this talk, which is the most important conjecture you've never heard of. Well, I can see some specialists in the audience, so some of you will have heard of it, but nonetheless. So let's start from the beginning. God created the integers, all the rest is the work of man. I want to throw a little bit of math philosophy in to explain how mathematicians think, except I don't really want to speak for all mathematicians. I want to speak for myself and perhaps for many people. And here's a quote which I think goes completely against how I think about mathematics. And I really want to explore the idea and the way that mathematicians think that's charged on the concept that math exists in this way that you have to go and discover, and some intuition for what might go on is almost more important than proving theorems. There's a lot of emphasis on proving things in mathematics, but there's a way of approaching mathematics as a physical science where you try to guess what the answer is and you do some tests, and your intuition built up in that way is almost more important than proving theorems. I mean, some of the most important conjectures in mathematics come from thinking about what might be true as opposed to kind of proving things. All right, so my talk is about pi. So let's give a definition of pi. It's the ratio of the circumference of a circle to its diameter. And to add to that definition, here's a theorem. is that the area of a circle with radius r is pi r squared. So every talk should have at least one proof. I'm going to give two proofs. The first one you probably know is you take a piece of pizza. So the circumference of the pizza, let's just say the radius is 1, so the circumference is 2 pi. And you cut it into very thin, annoying to eat slices of pizza, and then you rearrange it, and you more or less get a rectangle. And using that, you can compute that the area is pi if the circumference is 2 pi, with suitable scaling multiples of r if necessary. So this is a result that's been known for a very long time. So let's give some more facts about pi and get to the key aspect of pi that I want to delve into in this talk. So some familiar things. Here's pi to some number of digits. Some of you may know all of them. I think I know up to 9. Here's an approximation by Archimedes that pi is approximately 22/7. So questions of rational approximations to pi, this is exactly a problem that Kurt Mahler studied, understanding how close an approximation you could get to pi using numbers with small denominators. So here 7 is a particularly small denominator, and yet this approximation is very good. And understanding exactly how well you can do is still an open problem, but one for which the first key result was proved by Mahler. Lambert proved in 1760 that pi is an irrational number. That is, pi cannot be written as the ratio of two integers. So square root of 2, perhaps was the first number to be proved irrational by the Greeks. Once they discovered that the root 2 was irrational, they gave up number theory. They started to do other things. That's how upset they were. But already in 1760, this was kind of a very key result that resolved the question that implicitly was asked by the Greeks. There is a more sophisticated version of this theorem that pi is transcendental. So that's the claim that not only is pi not a ratio of numbers, of integers, which you can think of as pi satisfying a degree 1 equation. Say if pi is a on b, then b times pi minus a is 0. That's a degree 1 polynomial with integer coefficients. It's not a solution to any polynomial with integer coefficients. So it's even worse than the square root of 2. Here is the paper of Lambert, and I want to just point out a few remarks about it. The first thing that surprised me, which is not even mathematics at all, is the fact that there's a long S in French, which is maybe not so surprising because I don't really read 18th century French text very, very frequently. So let's just say, so the first line more or less says, proving that the ratio of the circumference of the circle to the diameter is not rational is something that's more or less obvious to geometers, rather something that geometers would not at all be surprised by, which is, I think, kind of underselling the result. But there's another remark which is related to that he later is talking about various sums. And so he's talking about if you take a sum, he gives an example here, and he says that if a sum, an infinite sum, turns out to be a rational number, then it's usually the case that that rational number is very simple. That it's usually in particular either an integer or a rational number with a small denominator. So philosophically, this is a strange thing to say. I mean, of course, you can write down any sum and make it sum to any rational number you want. But this is a kind of principle in mathematics that answers should be nice. And so if the answer is a rational number, well, it should be a simple rational number. And this is a way of thinking about something that, of course, is not anything related to proof, but it's a philosophy, it's a heuristic that is also underlying perhaps what the key point of this talk is. Okay, so here is a particular sum of which he gives the example of. This is actually a rational number, and it's equal to 1. Okay. So one thing that you know, if you've done any mathematics at all, is that pi turns up everywhere. So there are lots of formulas, not just by people who are studying pi, but even in ways that are perhaps surprising and unexpected. So here I'm just going to write down a few formulas for pi. One of the very first by Wallace is not an infinite sum, but rather an infinite product. Perhaps the more famous, maybe even the most famous infinite series that sums to pi is the formula of Leibniz, which is the alternating sum of the reciprocals of the odd numbers. So here's a formula for pi, or rather for pi on 4. But there are many other ways. I could fill an entire talk by writing down different sources of pi, but just to give one more, this famous theorem of Euler that e to the 2 pi is equal to 1. And so one question is, what does it mean that pi turns up everywhere in mathematics? So I think a good starting point is to think about pi and calculus. So let's start with the circle. We can think of as being given by x squared plus y squared is equal to 1. So using calculus, we can compute the area of the circle. Well, we want to take an integral of some function, so we need to write y in terms of x, and then write the corresponding integral. Well, if you write that integral, you only get half of the circle, so we have to multiply it by 2, and we get the following formula for a definite integral, whose answer should be the area of a circle. A slightly more complicated computation allows us to compute what the perimeter, or what the circumference is. If I take the circumference divided by 2, that's just the circumference of the top half. And instead of the integral of y, well, there's another way of computing the formula for arc length of a function, which is given by this integral on the left, which, when you go through and do the computations, you can also write as a definite integral from -1 to 1 of something that looks kind of similar, but is quite different. Namely, instead of the square root of 1 minus x squared, it's 1 divided by the square root of 1 minus x squared. So the theorem, already known to the Greeks, is that these two integrals are equal. In fact, both equal to pi. There's another thing one learns early on, or at least you learn it the hard way. When you're learning about calculus, you learn how to differentiate, and the process of differentiation ends up being given by a sequence of rules. And then you learn how to integrate, and integration is given by some sequence of tricks. And you have these tricks, and you try to do these substitutions. Sometimes they work, sometimes they don't. And even you get integrals which someone tells you that, oh, you can't even integrate this at all. It has no closed form. They don't usually tell you why, but you believe them. They're your professor. So there's some friction here, even though the fundamental theorem of calculus says that differentiation and integration are just inverses of each other. The actual process in principle of computing them really seems to be a little bit different. And so we can be led to this question of, instead of talking about pizzas and cutting them up, we could ask, just by using calculus, can we prove that these two integrals are the same? Well, I haven't quite told you the rules of the game. I mean, perhaps if you were doing this, you would say, well, let's just make some substitution, and you can compute both sides, and then you'd find that in both sides you got pi, and so therefore they're the same. And that's certainly a proof. But when I say this is I don't want to use some complicated substitutions using trigonometric functions and use various facts about the circle that reduce the problem to the theorem that I'm trying to prove in the first place. I want to use elementary calculus. So I want to just do substitutions of x by other polynomials or other simple functions. I want to integrate functions directly and not use trigonometry. And so here, well, really one proof is enough for a public talk. I'm giving two proofs, but I'm proving the same thing twice. So I think I can get away with it. So here's a proof that these two integrals are the same. Well, first I can take their difference. All right. And now the point is that even though these two individual expressions, they don't on themselves have simple integrals. I mean, you can integrate them in terms of inverse trig functions, but nonetheless, when you take this difference, you can directly integrate it. And in particular, now you can just evaluate the right-hand side at 1 and at -1. And you see in both cases you get 0. And so that proves that these two integrals are equal, but it proves it without using the fact that we wanted to prove in the first place. If you use inverse trig functions, in the end, you're secretly using the fact that this pi has two definitions that are equivalent in terms of the circumference of the circle and the area of the circle. And those two definitions, that you can't really give two definitions, you have to prove a theorem. So to actually give a genuine proof, you really have to do something a little bit like this. So here's a conjecture. Is that all equalities between integrals can be proved in this way. What are the rules of the game here? Here I'm thinking about definite integrals, and maybe I'm thinking about definite integrals which more or less involve either rational expressions in x or maybe algebraic expressions in x, exactly like what we had on the last slide. And when I say proved in this way, I mean proved in an elementary way by some combinations of various substitutions and algebraic manipulations, but nothing fancier than that. So here's another variant of that same conjecture, said in a quite different way, which is that any integral that involves pi secretly has a circle behind it. Right? If you have an integral that, for some reason, it's equal to pi, what this says is that, well, I have another integral that's equal to pi, namely the square root of 1 minus x squared, integrated from -1 to 1. And so this conjecture says that I can go from my integral and transform it to the other integral by a set of substitutions. And if you think about what that means algebraically, it somehow means that the function you're integrating to get pi involves the equation x squared plus y squared equals 1, maybe after some very complicated series of substitutions. And so this is maybe the kind of a meta conjecture that says, well, pi is turning up in lots of places, but at least if we restrict to integrals, which is a very broad class of things, because many infinite sums can be written as integrals, many things can be written as integrals, is that really all these sources of pi are not really different. They're all linked geometrically in some way to a circle. But there's an interesting corollary of this conjecture, which is to say that if I have an integral that doesn't involve a circle, then the evaluation of that integral has to be a number that can't have anything to do with pi. If I was getting pi, then, well, that meant I had to be able to go back by this conjecture to the circle. But if I can't do that, then I can't go back to pi, and then therefore the integral has to really be different. And so what that means is that I can start considering integrals, and I can ask questions. For example, is this integral, whatever it is, does it give me an irrational number? Does it give me something involving pi? And I can start to ask and maybe even answer questions about the nature of various numbers that arise in terms of these integrals. So a word for these integrals that is often used is the name period. And the reason why they're called periods, maybe this will come a little bit clearer, not much clearer, but a little bit clearer later on in the talk. So this is really the kind of main conjecture I want to talk about. And this is related to a very famous conjecture that I will come up and talk about a little bit more. Around about 20 years ago, the Clay Mathematical Institute released a list of 7 millennial problems, in which if you solve one of these problems, you get $1 million if you solve it to the satisfaction of a certain set of criteria. One of these problems, the Poincare conjecture, has been solved. The rest is still open. The Riemann hypothesis is certainly a famous one of these problems. But this is really about another of the problems on this list that if you see it, you'll probably look very boring. It's the type of actual conjecture that most mathematicians don't really have a sense of what it means. And I kind of want to explain that what's going on here, this is really somehow what this conjecture is about. All right, these are called periods. So here it is. I put these words in red because they're scare quotes. One of the Millennium problem involved is called the Hodge conjecture. So there are two conjectures. Actually, the Grothendieck period conjecture and the Hodge conjecture exactly predict that equalities of periods are geometric. So what do I mean? I mean, the conjecture that I gave you on the previous slide is exactly the combination of this very famous open problem, the Hodge conjecture, and another important conjecture, the Grothendieck period conjecture. It says more or less that if I have an integral and I have a second integral and they're equal for some geometric reason that you could explain, which you should more or less think of as some substitution that you can do that gets you from one to the other. Okay. So Hodge and Grothendieck, there's pictures of them. Grothendieck is perhaps a very famous mathematician, a French mathematician who really completely revolutionized much of number theory and algebraic geometry by introducing a set of algebraic ideas into geometry that hadn't really been studied before, at least not at the level of generality that he studied. And the amazing thing about Grothendieck's ideas is, on the one hand, they're very abstract and maybe a little bit hard to get into, but on the other hand, they're really ultimately kind of developed to solve very basic and elementary problems. So just to link both of them, he wrote a paper called, talking about the Hodge conjecture, that Hodge's general conjecture is false for trivial reasons, which is a slightly cheeky title. But there you can see, if you actually want a statement of the Hodge conjectures, there you go. Exactly. The cohomology class in a projective smooth connected scheme is algebraic if and only if it satisfies some certain criterion in cohomology. So that's what the conjecture is. But what you should really think about is exactly what I said on the previous slide. So let's talk about some other integrals. We talked about circles. Let's talk about an ellipse. If you take an ellipse, well, you can think about it as x squared on a squared plus y squared on b squared is equal to 1. You can compute the area of an ellipse. I think the area of that ellipse is pi ab. But the perimeter of an ellipse is a more complicated kettle of fish. If I take this particular ellipse, where I've just chosen it to be almost as simple as possible without being the circle, if you use the same formula for arc length to compute the perimeter, you get this unpleasant looking integral. And so you can ask, what is this integral? Is it related to pi? Is it a rational number? Is it a transcendental number? What's going on? How can I compute it? So let's go back to the circle. I told you that the geometry of the circle was key, that if any integral can be computed in a simple way and related to pi, it should have something to do with the circle. So let's tell you something about the circle and its geometry. So one very nice thing about the circle, which is an algebraic fact, is that you can parameterize this by a single parameter t. So what I mean by that is, for any t, in this particular picture, for any real number t, I can give an exact point on the circle as follows. I choose a point, which I choose to be -1, 0, and I take a line which has slope t. And that line, since it goes, any line that goes through one point of the circle will go through exactly another point on the circle, possibly the same one if it's tangent. And so for any t, any slope, I get a unique other point on the circle corresponding to that t. And so I can think of the circle as being parameterized by the single variable t that is unrestricted. And so you can actually use this in a practical way. Let me kind of actually write down the formulas if I solve the corresponding linear equations. Given t, that x is given by this formula, y is given by this formula, and you can check that these algebraic expressions do indeed satisfy x squared plus y squared equals 1. So again, I can think about this geometrically. I can also think about it algebraically. Just the equation x squared plus y squared equals 1. I can parameterize all solutions to that equation by a single number t in the following way. X is given by this and y is given by this. So this actually allows you to compute some integrals involving the circle by using substitutions that aren't trig substitutions. So here's an example. So I have an integral, say involves y equals the square root of 1 minus x squared. Then I can make a substitution by exactly the x and y that I had before. These x and y satisfy x squared plus y squared equals 1. So if x is equal to this, then y is given by that formula. And so then when you make the substitution, well, you get rid of your unpleasant square root term. And, yes. What I didn't write down was perhaps dx. But dx is also going to be some rational thing in terms of dt. So I could have taken my original integral with the square root of 1 minus x squared, made a substitution, and at least reduced it to something involving rational functions of t. Okay. And the key geometric point is that not all equations can be parameterized. So in particular, if I take this equation, you could ask a question: can I somehow think of all the solutions to this equation and parameterize them by a single parameter t? So in other words, can I find rational functions x of t and y and t that have the property that they satisfy this equation? So it's not so obvious how to answer that question. But the answer in particular in this case is no. And one way of thinking about that is that this equation is not related geometrically to the circle in the perhaps loose language that we've talked about. And so what that means is that the integral of this ellipse, of the square root of this expression that gives you this arc length of the ellipse, if we believe our conjecture, the perimeter of that ellipse should be a number that not only should be transcendental, it should have nothing to do with pi. That means it's not related to pi, even just as a multiple of pi. It shouldn't even have any algebraic relationship to pi whatsoever. A completely new number. And I put a star here on become because, of course, all of this is based on conjectures that have been around for 50 years and that, in some sense, we've made very little progress on. Okay. So I wanted to kind of try to explain a little bit about parameterization and what that means geometrically. And this is unfortunately going to have to involve thinking in 4 dimensions, because when we think about the equation x squared plus y squared equals 1, well, really we think about the circle and we think about x and y being real numbers. But if you're allowed to make substitutions, you really have to allow complex numbers as part of this game. And so you have to think about the equation x squared plus y squared equals 1, where x and y are both complex numbers. And then, well, if x is a complex number and y is a complex number, the set of solutions to that equation is not just in r squared, but rather in c squared. So you have to visualize what's going on inside c squared, which you can think of as r4, of what happens when I draw the set of solutions to this equation. And as a comparison, let's consider the solutions to the corresponding equation here. Well, I moved a 1 minus x squared from the denominator to the numerator. Since that only differs by a square, it doesn't change the intrinsic geometry of this question. So if I look at the solutions in R4 or in C squared to these equations, so you might ask, well, how do I think about an object in 4-dimensional space? Well, a circle inside R2 has dimension 1, because I'm considering one equation, x squared plus y squared equals 1. Inside the complex numbers, I really have 2 equations. I can say the real part is 0 and the complex part is 0. So inside R4, it should be some two-dimensional object. So the set of solutions inside R4, inside C squared to these equations, are some two-dimensional objects. And we can draw two-dimensional objects, at least inside R3, if not R4. And here's what happens when you draw them. So for the circle, as I said, it's parameterized by a single number t. So we're really thinking about a simple, single complex number t. So for various important reasons, we have to include points at infinity in scare quotes. And so what happens when you think of all complex numbers, which maybe you think about as a plane, you really have to add a single extra point at infinity, which turns that plane into a sphere. On the other hand, if you take this equation on the right, and you consider the solutions in complex numbers, and think what it is geometrically, it's not a sphere. In fact, it's a torus, surface of genus 1, something that is really fundamentally different from the sphere. And the fact that it's geometrically different is really somehow saying there are no circles going on in this right-hand side. That's the computation that proves, assuming the Hodge conjecture and assuming Grothendieck's period conjecture, that really the integral of an ellipse, the arc length of ellipse, is some number that's completely independent of pi. Well, you can also ask the question, well, if I take all these different ellipses, do I get something different for every possible value of a? So for a equals 1, of course, we get back pi. But for what about all the other a's? Well, for all the other a's, they have nothing to do with the circle. And so we get some number that should have nothing to do with pi. And by the way, we know enough about this particular situation to provably be able to say that the answers we get, for example, for the perimeters of these ellipses, are not only transcendental numbers, they're transcendental numbers that have no relationship with pi. But we can consider them. Let's kind of just use this parameter k. And now we can consider different values of k. And now the question about is, well, if I take two different values of k, rather than just kind of the case of the degenerate case of a equals 1, which is k is equal to 0, for these two different values of k at different ellipses, are there any relationships between the perimeters of different ellipses? So if we assume our conjectures, this then translates into some geometric problem that we can hope to solve. I think when it comes to kind of the number theory of numbers being transcendental, the basic principle has always been geometry is easier than number theory. It's very hard to prove something is irrational, but something geometric is a little bit more tractable, and that we can try and understand what happens when we take different values of k. And I think the first natural guess is to say, for all different values of k, these numbers are all completely unrelated. These should all be transcendental numbers that have nothing to do with each other. I think that's the natural conjecture. So let me just, for convenience, slightly change the function. Instead of exactly the integral for the primitive ellipse, here's a slight variant of the function where, again, I've moved the 1 minus x squared from the numerator to the denominator. These two functions are certainly intimately related, but it will allow me to say things without telling any tiny fibs. Okay. So in fact, it's true that if we choose random k and l, even random rational numbers k and l, then these numbers are unrelated. But you can provably show they're transcendental, they have nothing to do with each other. But it's not true that for all k and l, these numbers are completely different. There are some special pairs for which they are related. But here is the kk again. And here, for example, is the theorem. This due to Landon, again, 270 years old, is the following functional equation that relates two values of this function. So here one should think about this as follows, if we're going back to ellipses, is that for various pairs of numbers, I mean, the relationships between the a for one ellipse and the other a is very obscure. I mean, once you translate them back into k and then use this formula, various pairs of ellipses, their perimeters are related in some way that is sort of not at all clear from the geometry of the ellipse. Right? It's not really the geometry of the ellipse that's relevant here. It's the geometry of the expression that you're integrating namely the geometry of the function that you get by looking at y is equal to the square root, or rather the geometry of the equation y squared equals 1 minus x squared times 1 minus k squared x squared. It's true for all values of k, except for the exceptional one, that when you look at the solutions, you get the complex points look like tori, look like these donuts, surface of genus 1. But nonetheless, it turns out that not all of these donuts are the same, and for them to be geometrically linked is a more subtle business. And so you have this very strange behavior that for a single value of k, there are infinitely many other ellipses that have some relationship with it, but for all but those infinitely many, they're completely unrelated. And again, this is sort of the simplest historical case in which actually we know enough to have that these conjectures are really theorems. I should say another way that these integrals come up is not only for the perimeter of an ellipse, but also when you start to look at a pendulum and you take a pendulum swinging, and then you ask, well, how long does the pendulum take to swing? Or rather, what is the period of the pendulum? And so that use of period is exactly associated to these integrals, which were then called periods, which then can be generalized in many other situations. But again, that's kind of the source of the word period. So in the case of at least for ellipses and their perimeters, we have a satisfactory answer, not only conjecturally, but even theoretically. And it relates to the geometry of the equations given by y squared is 1 minus x squared times 1 minus k squared. This is Landon's paper. Interesting to read historical mathematics. You might think that, well, we've learned a lot in 270 years. It should be easy to understand, but the language in which it's written is very floral and confusing, and it's almost impossible, even if you know the result is proved in a certain paper, to even necessarily locate it inside the paper itself. So let's move on from ellipses, and let's move on to Euler. You can't have a math talk without talking about Euler. So there's a famous problem known as the Basel problem, since it was the town where the source of this problem came from, which is to evaluate the following infinite sum. It's the inverse sum of the squares. Numerically, it turns out to be 1.644, etc. And Euler investigated this problem, and he recognized the answer numerically to be pi squared on 6. So he first observed it was pi squared on 6 by recognizing the number, and then he gave a proof. So again, this is an infinite sum, but nonetheless, you can think of it as a period because many of these infinite sums are not so hard to convert to actual definite integrals. Okay. Well, that's Euler, and that's Basel. All right, so here's a way of converting an infinite sum into an integral. 1 on n squared. Well, 1 on n is just the integral of x to the n minus 1 from 0 to 1. So I put two of them together. That's 1 on n squared. And then I take the sum of all n. And then I change the order of summation from the integral to the sum. And I have a sum of powers of x, y to the n. And that's a geometric series. And I get the following double integral. And this exactly falls within the scope of things we're discussing. It's exactly a period, an integral of some nice rational function. But again, we will allow not just integrals, but even multiple integrals. So this is exactly something covered. I'm not sure if that's me or not. Exactly covered by this Grothendieck period conjecture. Okay. So also Euler, not only did he do the sum of the inverse squares. Well, if you do the sum of the inverse first powers, it's well known that that sums to infinity, but Euler also computed the sum of the inverse fourth powers and the sum of the inverse sixth powers. And in fact, the sum of the inverse 2n powers for every even integer 2n. And the answer in all cases was provably a rational multiple of pi to the 2n. And all of these numbers are periods because you can write them just by exactly the same procedure as some, maybe not a double integral, but a 2n-fold integral. But already from Euler's time, there's a very natural question left over from these computations, which is, well, you can compute the sum of the inverse squares and the inverse fourth powers and sixth powers. What about the sum of the inverse cubes? What about the sum of the inverse fifth powers? What are these numbers? Well, one thing you can do is you can define a function, the zeta function, Riemann zeta function, which by definition is the answer. Well, that's a kind of course, that's not an answer, but it's a way of writing it down. And so then the question is, what is zeta 3? And the first obvious guess is it should be a rational multiple of pi cubed. But following kind of the inspiration from earlier, if it should be a rational multiple of pi cubed, it should be a simple rational multiple of pi cubed. And you can compute it on Mathematica nowadays, or by hand if you were in the 18th century or earlier. And you find it doesn't look anything like a rational multiple of pi cubed. You compute the sum of the inverse fifth powers, it doesn't look anything like a rational multiple of pi to the 5. And I think that to a mathematician, even in Euler's time, and I would say 4 out of 5 mathematicians, at least on the street, if you told them the results of this computation, they would be very happy completely believing that zeta 3 is not a rational multiple of pi cubed. I mean, somehow, if it's going to be a rational multiple of pi cubed, it should be a simple one. And so, once you believe that, of course, you then believe it should be some crazy transcendental number that has nothing to do with pi. And so the whole game, the whole heavy work that the Hodge conjecture and the Grothendieck conjecture are doing is giving you a geometric language to really ask and answer this question. Right? Again, these are periods, because you could write zeta 3 as a triple integral. You can certainly simplify this triple integral in some ways. And then I have a period, and I want to say that this integral has nothing to do with pi. And so if I believe these conjectures, I'm reduced to a geometric statement that I have a hope of proving. And it's a little bit subtle to kind of write down exactly the geometry that you have to study in these cases, so-called mixed motives, but you can do it, and you can genuinely prove that on the geometric side, this really has to be independent from a circle. And so if you believe this conjecture, this is really a new number in mathematics. I mean, really, in mathematics, maybe to have a little bit of sympathy from the original quote, we start with the integers, and then you have some algebraic numbers, and then you have this pi that's a completely crazy, mysterious number, and then you get used to it. Right? You just write pi enough times, and you start to feel like you know what pi is because you see it a lot. Right? It's zeta 3 in some sense is just exactly that. It's a new number. You can give it a symbol called zeta 3. And I mean, pi was happily used for millennia, even though it could have been the case that pi was equal to 2217 plus some very small rational number. We're still happy writing pi, right? I mean, but the point is that we now know in the case of pi, and we certainly believe in the case of zeta 3, that it's a completely new number. And the reason that we are justified in that belief is we now have a formulation of a conjecture that reduces it to something that we can compute. Okay. So again, the period conjecture implies, by a computation that's certainly non-trivial, but certainly much easier than proving the conjecture, that there's no relationship, not just between zeta 3 and pi, but no relationship between any of these numbers, pi, zeta 3, zeta 5, zeta 7. Each of these odd zeta values, for every value, should be something completely new. If you go to kind of high school or kind of undergraduate online kind of websites like Math Overflow or Math Stack Exchange, where you have very bright undergraduates, there's a challenge, which is to compute zeta 3. Maybe there's just some trick that Euler missed, that you can compute this infinite sum in some explicit way just by a kind of neat trick that no one has also observed before. And of course, one can't yet rule that out. But the point is that what we now understand, or at least we kind of believe, is that really you shouldn't be able to do that. It's just a new number. We have to live with it. We can give it a name, and then so on. We have these future numbers that we could never say so much about. Right? And so in the case of elliptic integrals and the primitive ellipse, there the story is completely satisfactory. We really know that these numbers are independent of pi. We know exactly when the pair of numbers are related and how that relates exactly to the solutions to these curves. In this case here, we're completely lost. It was, in fact, not until 50 years ago that we even managed to prove that zeta 3 was irrational. In the result, that was somehow incredibly surprising. Well, the result was not surprising, but the proof was surprising. But even still, we don't know that zeta 3 is not a rational multiple of pi cubed, or pi to the 7 for that matter. We certainly fully believe it, but it's still completely open. Zeta 5 is even worse. For any of these future values, we don't know if any particular one of them is irrational or not. But again, I mean, mathematics, perhaps it's less about proving things and more about knowing what's true. And a good conjecture is very satisfying in that, at least, even if we don't know exactly how to prove it, we at least have some understanding of why we don't know how to prove it, or what is maybe really true in it. Yeah, also maybe I'm just repeating this. The naive guess is a rational multiple of pi cubed, but it's not known. But we can prove it. It shouldn't be the case, assuming it's our own conjectures. We can prove it some completely new number. But again, this remains an open problem. All right. Thank you very much.
Okay, so thank you very much for this wonderful talk. So maybe I can begin with a question which perhaps was worrying some audience members, I'm not sure, which is that you're computing the perimeter of an ellipse, and you said we get very special numbers in this way. But I thought that as we scale an ellipse, we can get any positive real number.
Yes. So when we compute the ellipse, we're putting in a number to start with, which is this number a. And so most of the discussion was maybe implicitly assuming that I was putting in a rational number and then seeing what I was going to get out. Now you can certainly put in any number as well, but then the game has changed a little bit. Then you have to allow yourself this extra number to play with. So maybe we consider an ellipse in which a was equal to e, for example. Right? And then the game we have to play sort of allows us to kind of put that number in. So there's something that one can say, but perhaps it would have been better to restrict to assuming a was a rational number.
Okay, so further questions?
You mentioned that if a number is not related to pi, then the underlying problem is not related to a circle. Now, your illustration was on the circumference of an ellipse.
Yes.
But as you mentioned somewhere along the way, the area of an ellipse is related to pi. So how can those two be consistent?
Yes. So the key point is, what is the geometric object you're comparing? So the geometric object is not the ellipse that you're starting with. It involves the thing that you're integrating. So when you integrate, you're not integrating, when you compute the perimeter of ellipse, you're not integrating the function of the ellipse. You're integrating whatever the arc length of the ellipse formula tells you, which is the square root of 1 minus x squared divided by the square root of 1 minus x squared on 2. And so that equation, y squared equals that, is not an ellipse. It's something more complicated. Whereas if you compute the area of an ellipse and you write down the integral, it will just be the square root of 1 minus x squared in the end. So yes, it's not sort of the original source of the problem. It's the integrand and the geometry of the integrand that is the key. I think that's the right integrand. I think that's the right word.
Yes.
So if I understood correctly, your conjecture is that if you write down pi and then zeta n for n odd, all of those numbers have no polynomial relation among them.
Yes.
Is that right?
Yeah.
Do you have any conjecture of what you get if you join all those numbers to the real numbers?
Well, I mean, they are all real numbers to begin with. right? Do you really mean real numbers?
Yeah, to the rationals, let's say.
Yeah, well, right. So I mean, so to say that pi is transcendental is to say that if I add pi to q, I expect that's just a polynomial ring. If I'm allowed to use the word, I know you know what polynomial ring is. So you, I mean, so of course, you just expect a polynomial ring in infinitely many variables.
Are there any more questions that don't involve the word polynomial? Yes?
I think Zoodle had proved that between psi 5
And 11.
11
Yeah.
there is one of those that's irrational.
Yes.
Has there been any improvement on that?
That more or less, no. And I should say that, like, one reason that I chose this as a talk is because some of my recent work seems to kind of give possibly new methods for attacking these problems, but no promises.
Maybe I could just emphasize how bonkers that situation is. We have two numbers in mathematics, and we know one of them is not rational. But we don't know which one. You know, it's a totally crazy situation. So at the back?
Yeah, I was just wondering, Frank, can you tell us about the historical definition of the actual word pi for this complex number?
Yeah, I mean, that's a great question. I think my history is not quite good enough to say it. I mean, there was I guess a mathematician called maybe Ludolphus, who computed many digits. And for some number of years, it was called the Ludolphus constant. I think actually, yeah, here in Lambert's paper, Ludolph's number more. So he refers in this paper to pi as Ludolph's number. And I think that more or less came about because, I mean, of course, how it was referred to, I don't exactly know the terminology, but at least it wasn't called pi at that point. I forget who was the person who first used that symbol. It's probably Euler. I mean, if you had to guess, it dates to at least post 1760. I think that the use of the letter pi is a 19th century. I wouldn't say affectation, but.
Maybe we have time for one more final question.
So with the geometric methods that you've been referring to in the lecture, so what is the sort of geometric techniques that you'll be able to study, like the integrals, so you'll be able to obtain some qualitative analysis of the integrals?
So like, what is the geometry that I'm kind of not telling you behind? Yeah, I mean, it's a little hard to kind of give an answer that doesn't use scale words, but maybe I'm allowed to say that in these cases, it's all about elliptic curves. Now, these involve ellipses, so it's the theory of elliptic curves. That's the non-informative four-word answer to that question.
So like it partially routes through like elliptic curves in order to obtain like the sort of answer.
Yeah, I mean, what happens is the geometry that you get up, that these things are elliptic curves. For each of these Ks, you get elliptic curves. And then for some of these Ks, these elliptic curves are related, and for most of these Ks, they're not. And so it becomes it's a question of algebraic geometry that's much easier to answer than the question number.
So, yeah, let's thank Frank again for this beautiful lecture.